Thank you for giving me this opportunity. Alright. My name is Nath. I am currently doing my postdoc as a collaborative project between Ecole Normale and Lyon. I recorded my PhD last year for my IT partners, and the work I am presenting here, that most of it I did in my PhD. So it's basically on frustrating and current for particles and eddies. Maybe a little bit more from the main theme of this conference, but let me try to motivate that make sense of what I do. So basically I'm doing a material transport in vortical flow. So here you can see like example like a microplastic concentration portion. And you can see basically we are releasing these kind of particles to the ocean, and you can see the concentration of it is changing with time, and spatial locations where they get lost with changing over time. Okay, so this is one of the application where I can, and another is like the one we are seeing in the morning session where we are seeing the drifters, which gives us some useful information about the flow field. You can see the very rough pattern of the path line of these drifters. So basically, we infer that flow field might be like business chaotic and absolutely kind of chaotic, and of course the flow is unsteady, and there are a lot of processes going in behind, and if the drifters are not exactly tracing out the flow in the background, are we seeing is it something to do with the flow, or it's some artifact because of the drifters are not doing a tracer behavior or something different because of the finite dimension? So these are some of the things that I can learn. Here you see this is another example. Like we can see the nice eddy in the ocean because of the plankton dispersion, and we see this like spiral arms, and is this really a structure of the vortex, or it's also some artifact because maybe the plankton is not quite tracing out the flow. So these are some points you can think of where my study can be applied. Okay, so this is another extreme scenario where like we are seeing in the ocean where the density of the background fluid, which is almost same as the particles present in it, but here it's a difference in the atmosphere, and we have dust particles in it, and the density ratio between the particle and the flow is like of 1,000 order of magnitude. Can also we see the particles are affected by this kind of eddies in the geophysical context. So what we know about surface systems, like we have a single vortex patch, and there's a particle that we just release it. So basically, there is a like a decaying vortex flow field outside, and what we know is that if it's a tracer, like the one in the blue color, it will just trace out the streamline. But if it's a finite inertial particles, it will deviate from the streamline over a finite time. It's the relaxation time of the particle, which is accounting for the finite inertial particle. And it's going to depend on the size of the particle squared and the density ratio between the particle and the background particle. And that's first level. So it matters like how dense the particle is compared to the flow, and how large it is compared to the flow structure. So now we have like two determinants, we have kind of a like vortex system, and the particles present in it will basically centrifuge away from this vortices, and they will accumulate into regions where it is less vortical, basically the straining regions in the field. And you can see in reality the vortices are not quite circular patches. They are, because maybe between the interaction with other vortices they have become some elliptic kind of eddies. And you can see there are regions where the particles get accumulated, not exactly in straining regions, but some rotating regions with the vortex. So these are like what we know. But the question is that if you have some kind of like elliptic eddy. What will happen? So that's what we are seeing. Like it's not quite axisymmetric vortex that we see in reality. It has slight non-axisymmetry to the vortex types. What is going to happen to the particles? Where they will go? Can we predict? So I start with some like minimal cost to do this. Like I consider a simple isolated elliptic vortex types. Some point become elliptic, maybe because of the interaction with some other evaluating. But now it is isolated vortex, and I have like particles around it. What is going to happen in these particles? So first of all, if we have a single vortex patch in a rotational background flow, it's going to self-rotate because of Pio's velocity will induce a like a self-velocity, and because of the anisotropic velocity distribution, it's going to self-rotate at a constant rate. Because it is an irrotational property, it is going to preserve its velocity, its 2D system. And basically, it's going to preserve its aspect ratio and size, shape, everything. Just rotate. So it's going to produce a unsteady flow field around it. The rotation rate is going to depend on how much vorticity it has and its aspect ratio. So basically, we know the solution of it. Relative to a vortex, basically, is going to create an unsteady flow field. So, but if you observe this flow field in the rotating frame of the vortex, you will see a steady flow field, and you will have streamlines, something like this. So you can see it's like a kind of tripod structure. So there is a central region which is cyclonic, and there is two like regions here and here they are anticyclonic. And if we find fixed points where the flow velocity becomes zero, there are 5 of them. And this is like an unstable center. These two, like C and D, are stable centers in terms of dynamic resistance. And there are A and D, they are kind of stagnation points connected by the separated lines. So this is the path. If you put some traces, they will trace out this basically string, because in the rotating frame, this is steady flow, so the path lines are equal to string lines. So they will just trace out this path. But I'm going to ask the question: what will happen to inertial particles? Like they have some finite inertia. How will they behave in this flow? Of course, we are expecting that they will be centrifuged away from central vortical because this is a like unstable center here. And unlike any other vortex, it should be thrown away because of the centrifugal effect that we have seen earlier. So, first of all, let me introduce the equation that we basically we are solving the reference equations. Central momentum is balanced by the force acting on it. And we are in the limit of like very small particles compared to the size scale of the let's say vortex. So basically compared to the Reynolds number, it's going to be very small. So we need to consider the Stokes drag, which is proportional to the slip velocity between the fluid and the particle. So they're not traces. So they'll have some finite deviation from the fluid velocity at the location of the particle. So this is the Stokes drag. And basically the Stokes number, basically the relaxation time scale with the vorticity of the patch. And we are going to observe this dynamics in the rotating frame of the vortex. So because of that, we need to include the centrifugal and vortical force here. Just for clarity, I am in a non-rotating background frame. I am in a F which is not rotating. This centrifugal and vortical is coming because I am observing this rotating vortex and dynamics in the frame of the rotating vortex, not because the Earth is rotating. So what I do is that I release the particles and for like at least the aspect ratio of the vortex, and I just increase the Stokes number of the particle. Basically, I increase the particle inertia and see what happens to them. So the general trend is there, the centrifuging effect. If you can see the spiral arms of the particles centrifuged away, but you see a pair of attractors where some of the particles will get clustered, and they are in the anticyclonic regions. And they are not by the center of the anticyclonic region because of the finite inertia. These centers they're getting attracted. There is a point of the finite inertial particle system in terms of dynamic resistance approach, and this is getting like more. if I increase the slope number. And so there is a critical particle inertia beyond which there is no attractor exists. So basically, saying that there are fixed points in the rotating frame of the vortex. We will where we will see that there are the particles get clustered additional to being sent to the. So and remember, we are in the rotating frame of the vortex. So in reality, what we are going to observe in the lab frame is that basically there are 4 rotating attractors like Lagrangian points in the planetary system, where some particles will get clustered, and they will just rotate with the central vortex and will just move like planet rotating around sun, something like that. So it's basically a fixed point attractors where the particles are getting clustered. And what we found is that there is some critical particle inertia. If the particle inertia is lesser than the value, which is basically fixed by the vortex aspect ratio. And if it is lesser than that, there are regions, additional regions where this particles can get clustered, other than the straining regions in the flow field. So that's good. But if we have more vortices, like right now we have only an isolated vortex patch. What is going to happen if we have other vortices nearby? For the first level approximation, we consider the interaction with other eddies as a like weak straining flow superposed over the system we had earlier. So that's what we are going to do here. First, let's understand what is going to happen to the vortex patch. So earlier we had a single vortex patch and it will rotate with the constant angular velocity, preserving its area outside its shape. So now what happens is that because of the weak straining flow superposed, this vortex patch is no more going to preserve its aspect ratio and shape, but its vortices is concerned. So its area is preserved. But now it will rotate with a non-uniform angular velocity, and its aspect ratios keep changing as per this equation, where R is aspect ratio, and theta dot is basically the angular velocity. So it's periodic, but it's not constant. And S is basically the scale gamma of the strain rate, external imposed strain rate. And then also we have a solution for the strain rate, and this is going to produce again an unsteady flow rate. Now, the interesting thing is that even in the rotating frame in the vortex, we will see the unsteadiness still being there. There is some unsteadiness which is remaining. So because of that, even for a tracer, it will see an unsteady flow rate. So because of that, its path lane is not going to be straight lines. So if we just do a point section, basically we plot the map of the path lanes, we are going to get dense subset in the plot near the saddles and the determining functions, basically indicating Lagrangian pairs of the tracer particles. So my question is that, so this is how we know, but my question is that what is going to happen because of the finite inertia, whether the finite inertia of the particles can suppress this chaotic nature, or does it enhance? So I do the same thing as earlier. We have this notifications in the rotating frame, but because now we are in the rotating frame with like non-uniform angular velocity, we need to consider this Euler force, which you usually don't need to take, but here being eddy. And even in the rotating frame, the flow is unsteady, so that time dependence is always there. So first I will show a case where the strain rate is peak. Like I fix the source number to be 0.1 and after ratio to 0.5. I have a big strain rate in most of 10 -2. So what you see is that something similar to what you have seen earlier. There is a centrifuging effect and attracted by the particles are taking state. But you see there's a wobbling of the attractor. Basically, it's not a fixed point attractor, but it's a limit set attractor. It's just whatever the fixed point was now moved into a limit cycle because of the pop bifurcation. And but we have a strong strain rate beyond some critical threshold. We'll see that completely the structure is going to be chaotic. So there is a chaotic attractor where these particles are now going to get attracted. indicating the transport of the particles in this force field is chaotic. So we did a Melnikov analysis and we found out there is a ratio between the strain rate versus the Stokes number. If it is less than a critical value, it is determined by the aspect ratio values. This is going to be like predict everything like periodic or non-chaotic dynamics. But if the strain rate is large enough, like its ratios beyond the critical value, then the dynamics is going to be chaotic. So, yeah. Then we take it a little further. We want to consider in realistic manner. Okay, there are more eddies than just modeling the weak flow. If we have many such vortices, what will happen? So we consider single model for that. Rayleigh vortex for which is like assuming that the vortices are reached a steady state and like arranged in equilibrium manner. So it's a static property, steady and steady in time and non-changing in time and space. In space, it has this periodicity and this like this dynamics and like this for a single model. If we have some profile like this, what is going to happen? So we just have the same equation of area, and now we are going to observe everything that happens. So we don't have any correlates or centrifugal errors. Just want to observe what is going to happen for this inertial particles in such a property. Does anything interesting for that? We found some interesting thing. So what I do is that I release the particles from a vortex in a cellular region and observe what is going to happen for 3 different cases. Like I have a Stokes number less than 1 by 4, greater than 1 by 4, and oral 1. But you see that when the Stokes number is less than 1 by 4, they are less inertial and some critical value. You see there is centrifuging effect from the central vortex, but they cannot cross the separate cases. They found it between the same cell by the separate cases. The Stokes number is larger than 1 by 4, you see they leak across, leak to the neighboring cells, but they don't disperse much. But if the Stokes number is forward 1, you see there are particles which can move across these vortices in a ballistic manner. So let me try to explain what is going on here. First, let's start with the Stokes number 1 by 4. Where does this particular number come? So you remember this equation we have here is just this Newton's equation, and we have this flow field and expelled. We just put that here. We come up with this coupled body, and it's non-linear. So then we try to so we cannot do anything with this non-linear thing at the moment. So but if you do this observation, the leaking happening when the Stokes number is little greater than 1 by 4 is very close to this stagnation region, where we can think of the flow is kind of linear. So your folks made this in the leading order, and near the vicinity of this region, you get like to decouple spring immersed damper system. None of the direction. In the other direction, kind of damping with a negative damping coefficient and physical, but we only care about this the real number. And what happens is that when the Stokes number is less than 1 by 4, actually the system is like overdamped. The phase-wise trajectories are exponential. But the Stokes number greater than 1 by 4, it's an underdamped system. The phase-wise trajectories are having this oscillating nature, and these oscillations cause the particles to cross the separate lines. And once they cross, they move to the next cell, and they move farther from the fixed point or the stagnation point. Then non-linear to the flow will take care of it, and it will add it farther and will move to the next cell. But it cannot keep moving. So that's what we are seeing. Like it will disperse to certain extent, and then it will stop. Basically, it is the dispersion system, so it's losing its kinetic energy. When the particle is stopped and captured by some of the stagnation point. But we are seeing when the Stokes number is order 1, like they are very highly inertial. Some of the particles can keep going, so they are gaining some kind of energy. So what is happening is that when the stocks are not run, so to analyze this, we initialize identical particles. Like we take a stock number of 1.18 here, for example, and identical particles in all aspects, just that they released at three different locations inside the same cell. And you can see what's happening to the three particles. They do three different the red one is basically moving across the vortices as exact manner, and the blue is just sort of an intersected kind of blue, and the green is just doing so if you just plot the Euclidean norm squared from the rotation it has started at this time, you plot the red one is the square, alpha is basically a long time, and for the green one it's t to the power 1, and for the blue it's t to the power 0 on average. So there are three different kind of dynamics will happen, and it depends on where the particles are started. So basically indicating the non-axisymmetry in the flow. They are initial condition dependent, and we have also done an analysis of this green particles, and we have found they have positive Lyon exponent indicating they are related to gravity. And so what we did is that we divided one of the cell and colors, like marking where what is the dynamics depending on where they are starting from, and basically the red region is indicating the basin for the particles which will end up in the ballistic motion, and the green is basically for the diffusing motion or the random walk motion, and the blue is for the trapped in linear cycle motion. And you can see the exponent PDF here, and this is alpha Stokes number 1.1, and we did this for the range of Stokes numbers, range of inertia of particles, and you can see all this which dynamics emerge somewhere after the Stokes number 0.77 and beyond, because before that Stokes number less than that 0.77 the particles will eventually get caught up in a fixed point, the stagnation point. They will not have this kind of ballistic diffusive dynamics. They will just disperse across some of the vortices, and then they will stop there because their kinetic energy is completely gone. But the Stokes number is large enough, they can do this kind of rich dynamics. They can move across the vortices. Some of them can do diffusive and ballistic dynamics. So all of this is done for the heavy particles, density ratio is very large. But we have recently extended the study for the finite density ratio particles, or only heavier than the background weight, not the lighter weight. I think we have considered the pressure gradient and Arden mass effect, and we extended this, and basically we have seen. So this is a fancy way of writing the density ratio, so that it will be bounded between 2/3 and 1, neutrally going to the very heavy limit. And we have this all the dynamics that we have I have shown earlier is still there, but at different Stokes versus our points. And one thing I may want to point out is that the finite density ratio is the green part is that if you remember they are doing the random walk is now changed to a level actually. So just to relate to it, what we have seen is that the initial condition is basically causing particles to do different kind of dynamics, and it says that particle dynamics is not according. Like if you take a time average and a space average, like a quantum average, this is the this assumption that we have. In a HIT, if you do that, this is going to be same. But in a flow with structures like this, like in a procedure stored turbulence, we cannot expect that, because that's what we have seen. If they are initial condition dependent, so we cannot always say that we take a time average and it's going to be equal to the space average. And in isostatics for particles, that cannot be true always. So with that, I just summarize basically what I have done is that I had a elliptical vortex patch, and we showed additional fixed points where the particles can get clustered in a vortex, depending on their magnetic inertia. And with the interaction with other particles, modeled with the single strain itself shows that there can be chaotic transport, and it anyway makes a regular transport. And with multiple cellular eddies, I have originally found the ballistic transport and the DC motion, and also the density ratio being taken account for kinetic density ratio. These dynamics still remain. Finally, as an overall summary is like the structured flows produce non-aerobic transport, unlike in physics. So with that, I also want to thank my PhD supervisor and board and the collaborator Melnikov and and thank you all for listening.